Moving right along, let's now pull it all together. Let's write it in the vector form. So we have du dt, the acceleration term, we divided by rho so that we have 1 over rho grad p here. This is a gradient of p, which is basically unit vectors and then dp dx, dp dy, dp dz, right? And the gravitational force is acting in the vertical direction, so it's got the z cap, which is the unit vector in the z direction, equals F, where we have taken F now as friction because the forces have been pulled on this side. This is typically how you write equations of motion in the climate business. Okay, so this looks fairly simple, almost scary simple, but actually when you expand it out, you see that you have three equations for momentum in each direction, F equals ma in each direction, and these are non-linear equations. Okay, this is some form of Navier-Stokes equation, which is a phrase you may have heard of. So they are not solved easily. There are special cases where you can solve them, and we'll see some simplifications which allow us to extract some simple solutions which are still incredibly insightful in terms of the physics they represent. But in general, even though this looks like one simple looking equation, when you look at this, it is fairly complex, and the basic equations that go into weather, climate forecasting, climate projections, etc. are these equations which are solved on massive computers by discretizing them using numerical methods and so on, because they cannot be analytically solved with paper and pencil. The other thing to note is, of course, our familiar equation in the z direction has this hydrostatic balance that we have been talking about before, which we say is valid on large scales, which obviously means that there must be some assumptions that allow us to ignore the dw dt term, which is these three terms, right? And we will see that, in fact, when you do the scale analysis, dimensional analysis, we will come back to our hydrostatic balance. Okay, so especially comparing, considering we have a shell of a fluid for atmosphere and ocean, and horizontal scales of motion are much larger than the vertical scales. We will recover that, even though there are people who hate hydrostatic balance. So nonetheless, there it is again, dp dz equals minus rho g. Remember how we had derived it, taking a air column, a stationary air column, balancing pressure and gravity, right? So in this case, dw dt is much less than the gravitational pull. So obviously we said convection has vertical velocities of upwards of 25 meters per second. That's not small, but they tend to be very small. So large scale system keeps adjusting back to hydrostatic. That's what allows us to do large scale balances. The other additional thing we should remember is our favorite reduced gravity. Why? Because we are in a stratified fluid, so every time we move our parcel, we're still talking about our parcel, it is moving in buoyancy relative to the buoyancy of the fluid that's above it, below it, and to the side, whatever, right? So it is the relative change in density and buoyancy that always matters. So it's not just that dw dt has to be much less than gravitational force, but it is that it's gravitational force times the relative change in stratification. So the reduced gravity is what matters. So dw dt has to be much less than g delta rho over rho. Okay, that's important to remember. So we will do a conservation of mass the same way we did the forces. So you have the same parcel here with the same corners. We're looking rho at the center, right in the middle, and you have rho u coming in. Since this is a arbitrarily small parcel, we are not showing the change in u here, but we will write soon the differences in this flux and this flux. So conservation of mass basically means unless there is a source and sink, mass has to be conserved as the parcel moves around. So there are flux of mass coming in, flux of mass going out in every direction, and they have to be conserved. How do we do that? We will see that soon. Maybe I'll do this in the next podcast, because this one has already gone probably a few minutes. So let me do that. Okay, but we are dealing with velocity vector, pressure, and density. So we will need conservation of mass, thermodynamic equation, and so on. That will give us the full set of equations as we will see.